Alright, hello everyone. So welcome back to my channel. Today I will solve a problem. Lexicographical smallest equivalence string. So for this problem, you will be given an string 1, string 2, and a string base, which is base string. Let's say we have string 1 is ABC, string 2 is CDE. We have A equals C, so the first character right here equal to the first character in a second string. And we also have the B equal D and C equal E, same thing. The second index of the string 1 and is equal to the second index of string 2. So as said, if two characters is equal, they are equal and they are symmetric. So if A equal B, it means that B equal A, and it's have a transitivity, which is A equal to B or B equal to C. It means that A equal to C, just like that. And then for you have some of the base string right there, so we're just trying to write it out. So we have our base string right here, right? So it's PARSE. So this is the base string. We have the Parker and Morris. So we have P equal to M, right? We have A equal to O. We have R equal R. Okay, R right here, R equal to R. We have K equal to R. We have E equal to I. And R right here is equal to S, right? And then they are grouping all of that in here for you. So when R equal to S, right? So they're grouping all of the group right here. So I just write down those group. Right, so I have M, P, I have A, O, I have K, R, S, I have E, and I, right? So they are this different group right here. Okay. You have a base string of parser, right? You will, so for this P character right here, since it is in, you can see P right here. So you can see it's in the BM group, and M is a smallest lexicographic order, right? So it should be M right here. For A, since A is in this group, so A is going to be the next one, and it's the smallest lexicographical order, right? So A right here, we have R. R is in K, and K is the smallest. So we put K in here. Same thing with S is in this group. And we also use, and K is the smallest. We have E right here. E is the smallest, so we put E. And then K is again smallest. R in here, right? So this is our result. And when I draw out the problem like this, you might see they form like a component like this, right? So the data structure we're gonna use is gonna be union find, right? Union. So arbitrarily, that is how we process the problem. We will just pass this two character from this two string to our union find, right? So we have right here we have M P A O K R S E I, something like that. We will have a bunch of letters right here, and we don't need to haven't grouped them yet. We just keep them like this. There's our initialize data structure. Then what we do is we're gonna go through the first two string right here, right? First two string, and then we start union each character. Let's say we would try to union M and P, right? And then we will try to union A and O, like single character inside of this two string. Okay. So at the end, when we have a group of M, A, O, K, R, S, and E, I, we just simply needs to loop through our base string, and we find our parent of this component. Okay, let's say we pass P, we find the parent of P is M. Okay, and it's raised to one question is what is the factor when we're looking for a parent. So since the problem is asked us to do lexicographical order smallest, our parent, let's in this case I choose I have to union, I have kr, right, and have s, right. We have to find out if it's k, you see k is smaller than s. So what we do is we're gonna plug s to k. So parent will always gonna be the smallest order. Okay, this is how we do it, and we're just gonna jump into the code, and I will explain meantime when I'm typing the solution out. So right here, let's keep it this way, right, and let's type it out. So as I said, we do have a union, and it's gonna be the data structure of union S1 plus S2, right? We're gonna union, we will initialize with all the character in S1 and S2. Oh, there's yeah, we have our result, which is gonna be initially an empty string for now with the length of the base string. Okay, let me just n equal to the base string, right? And is the length of the base string, so this one should look like this, and multiply with n plus 1, right? Yeah. And right here we're gonna go through every single character. So c1, c2 in zip. This zip function, it just grab the two s1 and s2 and then loop through both of it, like loop through both of it at the same time. So I'm gonna do union of c1, c2, and then for I in range of n, so we loop through our and then we have c equal to the string of I. Okay, and we update our result. Oops, it's gonna be union dot find. This find is gonna use the parent, like gonna find a parent of a node, right? And then in the end we just return join. We join that function in with our result. Okay, now we're gonna start our union find data structure. So union find data structure, so we're gonna do union. We have our init self string, right? Then we have our self parent of the a hash map right here, right? So for c in string, if c not in self dot parent, right? So if the character is not in the parent, we create that. So c dot parent, c equal to c. So the parent is of node is the parent of a cell. That's initially what we want in union find. Then we have our find function. So find cell dot node, right? If node not in self dot parent, we return that node. So in case, let's say our base string it have a character that is not in like the component. Let's say I will have an integer L, for example. It's not in here, so it just simply return L. Yeah, this is why it's here. I have the parent, which should go to the self dot parent. Oh, my bad. Node. I have a while loop, so y not equal to self dot parent itself. We'll shrink it, right? Self dot set of parent, right? And then we move our self, something like that. And at the end, we just return the parent right here. We also have our union function. So self, we have n1 and 2, node 1, node 2, right? You have p1, and we also have p2. We have our self 1, self dot find, and 2, right? And then if the parent 1 equal to parent 2, we return, there's nothing to do. If the parent 1, let's say graphical lexical order is smaller, is greater than the 2, we just put the parent 1 would be equal to the 2, right? If 1 is bigger, it should be a children of the 2. In the other case, we do the opposite. Self dot parent P2 go to P1. So this is the code. Let's try and run it. Yep, work. And the submit. Yep, also work. So the time complexity is gonna be, we loop through the string 1 2, so it's n1, right? We create a union, so okay, let's write down so I don't forget. So temp O, we loop through the string 1 and string 2, so it's gonna be O of string 1 plus string 2. Thing for this is loop through string 1, doesn't matter, we already looped that in the union function. We go through the base string, so it's gonna be plus the string, so base, and we call union find. So this union find right here, the worst case scenario is gonna be 26 character in one component, right? So that is the worst case, but because since we do this, we do like a quick pruning right here, would not be too bad. It would be like an optimized version of 26 base character. So the base string, right, multiply with 26, so it's just simply base. We join our result right here. So in total, we will have n plus m, which is gonna be n is string 1 plus string 2, and m is base string length. Then we have our space complexity. Our space is gonna be O of n, where n is string 1 plus string 2, right? Something like that. Oh, not really. It's probably just 26 character. So it's, yep. And try and see if it's worked. Okay, so basically I just run a little bit analysis on here just to find the right time and space complexity. So right here, as you can see, current complexity is n plus m. M is the 1 and string 2, as I said in my solution. So k right here is a base string, right? This alpha of k is the union function, right? This union right here. This alpha is only constant time, because the longest right here, you can say, you can use that, right? You could use an array of size 26 instead of a dictionary, right? So the worst case, when everything combined to one component, the space time complexity is going to be 26, right? It's going to be 26 right here, so it's a constant time. And where is it? Yeah, and also explain the space, it's only 26, not counting the result, so same thing, 26 is a constant time. Yep. And thank you for watching, and see you on the next video.